everyone, I'm Hannah Jasmine Santos and welcome back to my YouTube channel. So for today's video, we will now perform the experiment number 6, which is NAND gate as universal gate. The NAND gate is called a universal gate because it can be connected to other NAND gate or gates to perform any logic function. So let's go and start this experiment number 6, NAND gate as universal gate. Let's go! The equipment and materials that we will use in this experiment number 6 is first our power supply. Next is 1P74LS00 quad 2 input NAND gate, 1 piece 5mm red LED, our 1/2 watts 220 ohms resistor, 2 pieces SPDT switch, 1 piece breadboard, also our jumper wires here, and lastly our alligator clip. So let's start and construct this experiment number 6 NAND gate as universal gate. I will put this first. And I will open first this case of jumper wires. Then you can see in the circuit that the number 7 of the IC is connected in our ground. Here's the number 7. Then the number 14, which is this one, is connected to the positive side of our breadboard. Okay. Then our red LED, it is connected to the number 3 of our IC. Here is the positive and here is the negative one. So it is connected to our number 3, which is this one. Then the resistor also is connected to the negative side of our LED. And our resistor is also connected in our ground. So I will connect I will connect this 1, 2, so here I'm gonna press this down. Okay, then as you can see, the number 1 and the number 2 of the IC is connected in our switch. So I will place the switch here in the top. Okay, then I will connect this by jumper wires, the number 1 and number 2. So here is the number 1 and the number 2. So this 2 is connected in the center of this switch. So here and also this one. Okay, then the switch is also connected to the positive and also to the negative side. So I will connect this. To this side, to the here in the positive side, then the other one, which is this side, is to the negative. So I will connect that by using this. Okay, then I need to push this. Okay, so I think we're done with the figure A. Let's check. The number 1 and number 2 of our IC is connected to the switch. Then the number 3 is connected to the positive side of the LED. Then the negative side of the LED is connected to the resistor, and our resistor is connected in our ground. The number 7 also is connected in our ground. Then the number 14 of IC is connected to the positive side. Then our switch is connected both in negative and in positive side. So let's check. Let's connect this in our power supply. By using the alligator clip. And I will put this here and to the other side. So let's check what will be the output. So here you can see that the LED is turned on after we open the power supply. So in our truth table A, when our input is at logic 0, which is this one, our output then is at logic 1. And when our input is at logic 1, our output now is at logic 0. So that's all in the figure A. Let's proceed now to the second figure. So now let's proceed to our second figure, which is figure B. So as you can see in the circuit, there must be changes in the connection of the switch, because we will add one switch here. Then the connection of 4 and number 5 of the IC, and the number 6 will be the one which is connected in our LED. So let's make this second figure. I will remove first the other parts. So here I will remove this also. So I will add a switch. So in the circuit, the number 1 is connected in our switch A, and the number 2 is connected in our switch B. Then the number 4 and number 5 is connected to the number 3. Number 3, which is this one. It is connected to the number 5 and number 4. And also the number 6 of our IC is the one which is connected in our LED. And of course, I will back our resistor. So that's the switch. Here in the second switch, I need to connect this also to the negative and to the positive side of our breadboard. Okay, then also to the positive side. Okay, so now let's connect this in our power supply. So you can see here that our switch is both in at logic 0. So what will happen when we turn on our power supply? So let's check our truth table for this figure. If both switch, which is switch A and switch B, is at logic 0, our output also is at logic 0. But when switch A is at logic 1 and switch B is at logic 0, the output also is at logic 0. And when we change by making the switch B at logic 1 and switch A at logic 0, the output also is at logic 0. But when we make this both switch at logic 1, our output will be at logic 1. As you can see in our figure A that we performed earlier, using 2-input NAND gate, that logic circuit is equivalent to a NOT gate. And in the figure B, using 2-input NAND gate, our logic circuit is equivalent to an AND gate, 2-input AND gate. So, after we perform that in our breadboard, let's check in our logic gate simulator what is the design of a logic circuit that we can perform other logic function using NAND gate, like XNOR, XOR, OR gate, NAND gate, NOR gate. So let's perform this in a Logas application. So here we will go now to our Android to logic gate simulator to perform this other logic function using 2-input NAND gate. So first we will go to our application, then using 2-input NAND gate, design a logic circuit that is equivalent to a 2-input OR gate. So we will name it as NAND OR. So we will use a NAND gate to perform 2-input OR gate. So we need 3 of these NAND gate. And a 2-input and 1 output. So how we will connect this one? So this 2 is connected to this switch, and this 2 also is connected to this switch, and this one to the, and this is to the output. So let's check what is the rules in OR gate. So in OR gate, output is at logic 1 when one or more of its input are at logic 1. If all the inputs are at logic 0, the output is at logic 0. So let's check. So here, our output is at logic 0 because our switch A and switch B is at logic 0. But when we turn on the switch A and the switch B is at logic 0, our output now is at logic 1. And the other one, when our switch B is at logic 1 and our switch A is at logic 0, our output now is at logic 1. And when our two switch is at logic 1, our output is at logic 1. So that is now equivalent to OR gate. So let's save. Next is using 2-input NAND gate, design a logic circuit that is equivalent to a 2-input NOR gate or not OR gate. NAND NOR. So here we will use again a NAND gate to perform NOR gate. For now, we need 4 of these. 4 NAND gate. And also 2 input. 2 toggle switch. And 1 output green lamp. So how we will connect this one? Of course, again, this 2 is connected to this switch. And this is connected to this one. And this 2 is connected to this one. So we will connect this to our output. So in NOR gate, output is at logic 0 when one or more of its input are at logic 1. If all the inputs are at logic 0, the output is at logic 1. So now we will check this in our truth table. So what will happen when we run this? So you can see here that when our input is at logic 0, the switch A and the switch B, our output now is at logic 1. And when we turn on the switch A while the switch B is at logic 0, our output is at logic 0. And the other one, when we turn on the switch B and when the switch A is at logic 0, our output also is at logic 0. And when we make these 2 switch at logic 1, our output also is at logic 0. So that is NOR gate using 2-input NAND gate. So next, let's save this one. Next is using 2-input NAND gates, design a logic circuit that is equivalent to a 2-input XOR gate. So we will now design a logic circuit that is equivalent to XOR gate. NAND XOR. So click check again. So here we will use again 4 NAND gate. And the last one. So we will input again toggle switch, 2 toggle switch, and 1 output. So let's choose a red lamp. So we will need to connect this for us to get a result of an XOR gate. So how we will connect this one? So here, this one is connected to this switch, and this also is connected to this switch, and the other one is connected to this one, and this two is connected to this NAND gate, and of course we will connect this in our output. So in XOR, it says that output is at logic 1 when one and only one of its input is at logic 1. Otherwise, the output is at logic 0. So here in XOR, we will run this now. After we run this, okay, let's check. So when our input, when our 2 switch is at logic 0, our output is at logic 0. But when we turn on the switch A, while our switch B is at logic 0 and our switch A is at logic 1, our output is at logic 1. And when we turn on our switch B, while our switch A is at logic 1, when our switch A is at logic 0 and our switch B is at logic 1, our output is at logic 1. And when we turn all this switch to at logic 1, our output is at logic 0. So that is XOR gate. So let's stop and save this. So next, the last one is we need to design a logic circuit that is equivalent to XNOR using NAND gate. So here in XNOR, we will use 5 NAND gate. So this video of using NAND gate create a XNOR gate, I uploaded it also yesterday because it is a request of one of our subscriber, no? We need 5. Okay, so let's connect. Oh, we need output and input, of course. 2 toggle switch and 1 output. yellow lamp. So I use yellow lamp here. So how we will connect this one? So here, okay, so this one is connected in the bot switch, and this is connected to this one, and also this one. And this one is connected to our switch B. Let's adjust it for you to see the connection. And this one is connected to this, and this to this. Okay, then it is connected to this one, so you can see. And finally we will connect this in our output. So what is the description when we say XNOR gate? So in XNOR gate, output is at logic 0 when one and only one of its input is at logic 1. Otherwise, the output is at logic 1. It is similar to the XOR gate, but its output is inverted. So let's check. Let's run. So you can see that when our switch is both at logic 0, our output now is at logic 1. But when we make switch B at logic 1 while switch A is at logic 0, the output is at logic 0. But when again we make the switch A at logic 1 and switch B at logic 0, the output is at logic 0. But when we turn both switch at logic 1, our output now is at logic 1. So that is the sign of how two input NAND gate is equivalent to an XOR gate. So let's save. And we're done. So that's all for today. I hope you learned something new about this experiment number 6. Don't forget to subscribe and like this video. Thank you.